Hi students, in this session we are going to deal with the chapter carbon and its compounds. As you all know, carbon is a very versatile element, the sixth element in the periodic table. It has electronic configuration 2, 4. It is a non-metal and tetravalent, making 4 electrons available to form covalent chemical bonds. Apart from these, it has a wide range of properties and wide range of uses. Also, different types of isotopes are available for carbon, making a wide range of properties to use in the daily life. Diamond and graphite. Both of these are the two main allotropes of carbon. The physical properties of carbon vary widely with the allotropic form. As you can see here, graphite is a soft substance which is used in pencils. It is a poor conductor of electricity. Diamond is the naturally hardest substance known ever. As you can see again, graphite, diamond and fullerene. These are the three distinguished allotropes of carbon which mainly differ in their main structures. Next, let's see how the bonding takes place in carbon, the covalent bond. An element forms a compound by attaining its fully filled configuration on its outermost shell. This is the particular category which every atom of an element takes. That is a tendency or that is a reactivity of the particular element. As we have studied what is an ionic compound, as you can see here. In case of ionic compounds, the elements achieve this by gaining or losing electrons. As you can see in the picture, this is the formation of sodium chloride. Sodium losing one electron and chlorine gaining the same electron. They are forming sodium chloride Na plus Cl minus electrostatic bond of attraction. But coming to carbon, if carbon was doing such a way that it was to gain or lose electrons, there are two simple ways to understand that concept. By implementing the same two element carbon, it could gain 4 electrons forming a C4 minus anion, but it would be difficult for the nucleus with 6 protons to hold on to 10 electrons, that is 4 extra electrons. This means that carbon already has 4 electrons. Attaining 4 more electrons just breaks the electrical neutrality of the atom, which brings 4 protons against 10 electrons. This breaks the electrical neutrality and hence it is unstable. Similarly, carbon could lose 4 electrons forming C4 plus cation. Just as we discussed, this is also an unstable state, but moreover, it would require a large amount of energy to remove 4 electrons from the outermost carbon's shell. So, C4 minus anion and C4 plus cation is very difficult to form. In such a way, carbon overcomes this problem that it shares its electron with other atoms of carbon or other atoms of other elements. The shared electrons are now belonging to the outer shell of both the atoms. For example, if this is carbon and this is oxygen, they share their electrons such that both these atoms achieve their outermost octet noble gas configuration. Coming to an example, let's understand the concept of covalent bonding now. As you can see, there are two elements A and B, both having 7 valence electrons in their outermost shell. For A, it needs 1 more electron to achieve the noble gas configuration. So as for B. This is done in such a way that, as we just discussed, the single remaining electron for both atoms, they share the electrons such that A now has 8 electrons surrounding it and B also has 8 electrons surrounding it. As you can see, one pair of electrons is shared between A and B. Not just carbon, many other elements form covalent compound. So this is the concept of covalent bond. Now let's look at different molecules which are formed by covalent bonding. The simplest one is hydrogen. As you all know, atomic number of hydrogen is 1, number of valence electrons 1. So for hydrogen, the outermost shell, the outermost configuration which it needs to fulfill is to have 2 electrons. Hydrogen already has 1 electron, it needs 1 more electron. So 2 hydrogen atoms come closer and 1 pair of electrons is shared. Now both the hydrogen atom has 2 electrons surrounding it. In such a way, covalent bonding is occurring in hydrogen atom. So H2 molecule is formed. As you can see here, it is a single bonded molecule. Number of electron pairs is 1. Number of electron pairs is directly proportional to the bond. For one pair, it is single bond. Next, oxygen. Atomic number of oxygen is 8. There are 6 valence electrons in oxygen. As you can see here, oxygen needs 2 more electrons to satisfy or fulfill its noble gas configuration. So here, when oxygen comes into action for the compound oxygen gas O2, 2 oxygen molecules come together and the 2 electron pairs are shared between the 2 oxygen atoms, hence forming O2 molecule. As you can see already, there are 2 electron pairs shared between 2 oxygen atoms, so this is a double bonded molecule. Similarly, nitrogen, N2. Atomic number of nitrogen is 7. Number of valence electrons, 5. So, for one nitrogen atom, 3 more electrons are required to fulfill the noble gas configuration in its outermost shell. 2 nitrogen atoms come together and 3 pairs of electrons are shared between both the atoms. Now, both the atoms satisfy or fulfill the noble gas configuration. As you can see, the 3 pairs of electrons are there. So, this is a triple bonded molecule. As you can see in the picture, N triple bond N. Next, the simplest carbon hydrogen compound. Simplest carbon covalent compound, methane, CH4. Valency of carbon is 4. Similarly, valency of hydrogen is 1. As you can see, to achieve the noble gas configuration, one carbon atom shares with 4 hydrogen atoms, which means one hydrogen atom requires only 1 electron. There are 4 electrons in carbon, so one hydrogen atom comes to carbon and one hydrogen atom achieves the noble gas configuration. In such a way, 3 more hydrogen atoms comes to carbon and totally 4 hydrogen atoms comes around carbon and shares the electron, making carbon and hydrogen both together fulfill their noble gas configuration. As you can see, there are single electron pairs donated between each donation site, which means there are 4 single bonds. These kind of compounds are called covalent compounds. They have strong bonds within the molecule, but intermolecular bond strength is too low, which means a single molecule is very strong, 2 molecules is not strong. So therefore, their boiling points and melting points are really low. Here, electrons are shared, so ions are present. Therefore, these are poor conductors of electricity. For electricity to conduct, ions must be able to free flow. Here, it is not possible. The electron dot structure. It is the simplest depiction of a compound showing the bonding in it. It is also called Lewis dot structure. Just we discussed how covalent bond takes place in hydrogen, oxygen, nitrogen and methane molecules. These kind of compounds. As you can see in the picture, the electron dot structures for hydrogen, oxygen and nitrogen molecules are here. By separating the bonds, we have substituted the electrons that represent the bonds. So this is a simple electron dot structure, which means substituting the bonds, we directly put electrons that shows the linkage between 2 atoms. Covalent bond and dot structure of CO2, carbon dioxide. Just keep in mind a small idea. If you know the formula of the compound and if you understood the concept of covalent bonding and sharing of electrons, you can easily draw the electron dot structure of that compound. Let's put that idea here. Here we know that valency of carbon is 4, valency of oxygen is 2. So coming to this, one oxygen requires 2 more electrons to fulfill the noble gas configuration. One carbon requires 4 more electrons required to fulfill the noble gas configuration. So here coming to action, one carbon shares its 4 electrons with 2 different oxygen atoms, as you can see from the formula CO2, and here 2 double bonds are formed because between one C and one O, 2 pairs of electrons are shared resulting in a double bond between one C and one O. So O double bond C double bond O. This is the structure of carbon dioxide. Versatile nature of carbon. As we have studied till now, carbon has enormous and large number of properties and different kind of application, which is ranging from a small part to bigger part of wide range around the world. In this unique ability to form bonds with other atoms of carbon, it gives rise to a large molecule. This property is called catenation. As you can see in the picture, carbon is capable of forming long chain carbons, branch chain carbons, and even carbon atoms arranged in rings. In addition, carbon atoms may be linked by single, double or triple bonds. This special property is called catenation. Similarly, carbon has a valency of 4. It is capable of bonding with 4 other atoms of carbon or other atoms of other elements. Also, thus enabling carbon to form different kind of species with different properties. Compounds of carbon are formed with oxygen, hydrogen, nitrogen, sulfur, chlorine and also many other species. These different kind of species gives different determinant properties for that compounds. Now, we are going to deal the most relevant topic in this chapter, hydrocarbons, organic chemistry. As the name gives, hydrocarbons are the compounds formed by carbon and hydrogen. The peculiar field of study that deals with the study of hydrocarbons are organic chemistry. As you can see in the chart, hydrocarbons are mainly classified into saturated and unsaturated compounds. Saturated hydrocarbons means the compounds are single bonded compounds. In unsaturated, there are double bonded compounds and triple bonded compounds. Single bonded compounds are called alkanes, double bonded compounds are called alkenes, triple bonded compounds are called alkynes. As you can see in the next chart, there are 3 different kinds of formula for alkane, alkene and an alkyne. For alkane, it is CnH2n plus 2. For alkene, it is CnH2n. For alkyne, it is CnH2n minus 2. Which means, if we know the number of carbon atoms, we can directly determine the formula of the species. The type of bonding is, for an alkane, there exist only single bonds. For alkene, at least one double bond is present. For alkynes, at least one triple bond is present. Similarly, the naming comes such that the name alkane has the suffix ane, which is added to the word root. Similarly, alkenes end with ene. Alkynes end with yne. In the last column, you can see 3 different examples: methane, ethene, ethine. So these are the basic 3 categories of hydrocarbons. Now, general nomenclature. We need to name different class of compounds, right? So, for different number of carbon atoms, we have different word roots which are added as prefix and which is followed by a suffix. As you can see here, the alkanes ane, alkenes ene, alkynes yne. So, first let's study the number of word roots. If there is one carbon atom, the word root is meth. For 2 carbon atoms, eth. For 3 carbon atoms, prop. For 4 carbon atoms, but, pent, heps, hept, oct, non and dec. So these are the 10 main word roots. For alkane, the word root comes added by the suffix as methane, ethane, propane, butane, pentane, hexane and so on. For alkene, it is ethene, propene, butene, pentene, hexene and so on. For alkyne, it is ethine, propyne, butane, pentane, hexane, etc. So, in such a way, nomenclature is assigned. Drawing structures. Let's discuss the drawing with different examples. First, let's look with ethane. So, we just discussed the formula of alkanes. For alkanes, the formula is CnH2n plus 2. For ethane, number of carbon atoms is 2. So, the formula becomes C2H6. Different steps are Step 1, as you can see, linking carbon atoms together with single bond. There are two carbon atoms. We are linking the two carbon atoms with single bond. Step 2, using hydrogen atoms to satisfy the valency of carbon. There are 6 hydrogen atoms. So we are placing the 6 hydrogen atoms by single bonds on the carbon. Now, we must check the valency of carbon. As we can see, the valency of carbon is 4. It is satisfied. Similarly, the valency of hydrogen is also satisfied. This is the structure of ethane. Now let's look for another example. Ethene. The general formula being CnH2n, C2H4. Just as we said, we are doing the single bond first, linking carbon atoms with single bond, C, single bond C. There are 4 hydrogen atoms. We are using the hydrogen atoms to satisfy valency of carbon. We are placing the hydrogen atoms around carbon atoms. The 4 hydrogen are finished. Now, the last step, finding the satisfactory carbon's valency. Viewing here, carbon has only valency of 3. Carbon must have valency of 4. This can only be compromised by putting a double bond between the 2 carbons. So, the final structure CH2 double bond CH2 is the structure of ethene. Now, as you can see in the picture, this is a chart showing different kinds of alkanes starting from methane. Methane, ethane, propane, butane, pentane and hexane. If you just look with applying the formula CnH2n plus 2, you can also deal with the formula of the different compounds. The structure are also seen here. Structural isomers. As an example, let's consider butane. Butane means 4 carbon atoms, CnH2n plus 2, which is giving C4H10. There are 2 possible skeletal carbon structure. One is drawing the carbon structures in a straight chain C, 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 all having single bonds. Another possibility is drawing the structure as you can see in the picture, C and C, 2 carbon in one line and 2 carbons as diagonals. So, which means the same formula of carbon atoms have 2 different skeletal structures. Adding hydrogens, the formula also remains the same. As you can see in the picture, both the structures have C4H10 formula. These kind of compounds having identical and same formula but different structures are called structural isomers. This is a particular classification of the hydrocarbons. For another example, let's look with normal pentane, C5H12. There are 3 possible isomers for pentane: isopentane, neopentane and normal pentane. Example 3, hexane, C6H14. As you can see here, there are 5 possible structural isomers for hexane. Normal hexane, 2-methylpentane, 3-methylpentane, 2,3-dimethylbutane, 2,2-dimethylbutane. This is the line and dash form of drawing carbon molecules. Next, functional groups. Apart from hydrogen, carbon also forms bonds with other type of elements like halogens, oxygen, sulfur, etc. Here too, valency of the carbon is satisfied. In this case, as we just discussed, hydrogen is replaced by another atom. This atom is called heteroatom. This particular atom determines the specific properties of that particular compound regardless the length and nature of the carbon chain. So, these species determine the properties of that compounds, hence these species are called functional groups which functions the compound's properties. As you can see here, there are 5 different kinds of functional groups: halogens, alcohol, aldehyde, ketone and carboxylic acid, where aldehyde, ketone comprisingly is called carbonyl compounds. Among halogens, we add suffix chloro, bromo, iodo, etc., generally halo, to the compound. For alcohol, we are adding suffix ol. For aldehyde, we are adding suffix al. For ketone, we are adding suffix on. For acid, we are adding suffix oic acid. If you just look at that sample, for a hydrocarbon with functional group halogen like chlorine, the compound here is propane, which is having chlorine atom replacing one hydrogen atom. The compound is chloropropane, which means halopropane. Similarly, the hydroxyl compound, which means the alcohol is coming. Now the compound is propanol. Similarly, for aldehyde, it is propanal. CHO group has come into action. The next, for ketone, it is propanone. CO group has come into action. So, the next final one is propanoic acid, COOH. So, summarizing, we can see halogen group here is Cl, alcohol group is OH, aldehyde group is CHO, ketone group is CO, which peculiarly comes in middle of two carbon atoms, and finally COOH, carboxylic acid group. So these are the 5 different functional groups that specifically determines the chemical property of a particular compound. Let's look with some examples. For haloalkanes, first one is chloromethane. If we just recall the structure of methane, CH4, here one Cl has replaced one hydrogen atom coming CH3Cl. So that is chloromethane. Same is the case with chloroethane. One hydrogen atom is replaced from ethane molecule forming CH3CH2Cl. Next is alcohol. First one is methanol. As we just discussed, not chlorine, here oxygen and hydrogen, OH. This particular group is called hydroxyl group. OH group replaced hydrogen forming CH3OH. This is methanol. Similarly, OH has replaced hydrogen from ethane molecule becoming ethanol, CH3CH2OH. Now, the most important one, aldehyde. First one is methanal. The functional group of aldehyde is CHO. Just observe the CHO part. We can see carbon requires one more additional valency. 2 is given for oxygen, 1 is given for hydrogen, which means one more valency is there. We are going to fill that part with hydrogen, which gives the first compound HCHO, which is HC double bond H. This is methanol, also called formaldehyde. Similarly, replacing with CH3, the hydrogen earlier, we are getting CH3CHO. This is ethanol. Same is the case with ketone. In the case of aldehyde, we replaced CO with H and H in two sides. Here we are giving CH3 on one side and CH3 on other side, which gives CH3 C double bond O CH3. This compound is called propanol. CO bond is coming between two different carbon atoms. Same is the case with butanol, as you can see from the picture. Next one is carboxylic acid. Along with C double bond O, an additional hydroxyl bond is here, which means C double bond O OH. As we just discussed with the case of methanol, if we just observe the COOH only, there is one more additional valency for carbon which is required to fill. This is taken for hydrogen and the compound is formed as HCOOH, which is HC double bond O OH. This is methanoic acid, also called formic acid. Same is the case with ethanoic acid. You can just see from the picture. Homologous series. We just discussed the presence of a functional group determine the properties of the carbon compound. The homologous series is a sequence of compounds with the same functional group and similar chemical properties in which the different members in the series differ by a CH2 unit. For example, the series of primary straight-chain alcohols, methanol, ethanol, propanol, butanol, pentanol, etc. has hydroxyl compound like OH. The hydroxyl OH is the main functional group here, which determines solely the chemical property of that compound. The properties typically change gradually, which arises from the different molecular mass differences and also the length of the carbon chain. Thus, in a homologous series, physical properties changes gradually. On the other hand, chemical properties won't change because it is solely determined by the functional group. As you can see in the picture, this is the homologous series of alkanes, starting from methane, ethane, propane, butane, pentane, hexane and so on. One by one, these molecules differ by a CH2 unit. The physical property of each molecules differ, but the chemical properties remains the same. Similarly, the same for alcohols, methanol, ethanol, propanol and butanol. The physical properties like melting point, boiling point, solubility etc. changes accordingly since there is a difference in molecular mass and also the length of the carbon chain. But since all these compounds are alcohols, the hydroxyl compounds, the chemical properties remain similar. Same is the case with carboxylic acid, as you can see here, methanoic acid, ethanoic acid and propanoic acid. Next, nomenclature. The different steps involving nomenclature of the carbon compounds are: Step 1. Identify the number of carbon atoms in the compound. We already discussed the word roots for different number of carbon atoms. Step 2. If the carbon atom is saturated, A and E, alkanes A and E is added to the word root, which means if there is 2 carbon atoms and it is saturated, the compound will be eth ANE, which is ethane. If the chain is unsaturated, the ANE is replaced by ENE or YNE. If the ethane is unsaturated, which means the C double bond C is present, it is ethene. If it is C triple bond C, it is ethyne. This shows the double and triple bonds. Step 3. If there is a functional group, a prefix like halo, chloro, bromo, etc. or a suffix like ol, al, on, oic acid, etc. is added. If the name of the functional group is a suffix, the name of carbon chain is modified by deleting the last E. As you can see that symbol, just imagine we are writing propanon. Propanon is the ketone of propane. So propane minus E gives propan plus ONE, which is propanon. So just like that, the nomenclature is assigned. As you can see, there are different classes of functional group here and different compounds. So let's just look at the naming. First one, halogen. In this category, we have chloropropane. We are first looking the number of carbons. There are 3 carbon atoms here. So the word root is prop. It is saturated, so propane comes. But there is a functional group here, chlorine. So the compound name comes chloropropane. Similarly, bromopropane. The next one is alcohol. As you can see, when we look the number of carbon atoms, it's again prop. The functional group is OH. It is saturated, so we just look with propan and we add a suffix ol. Now propanol. The same is with aldehyde. The functional group is CHO. Including the functional group, the number of carbon atom is 3, hence prop. It is saturated, so it is prop plus ANE and it is having a functional group CHO. So prop plus ANE plus AL, which gives propanal. Similar is the case with propanon. When it comes with a double bonded compound, it is propene. When it comes with a triple bonded compound, it is propyne. Now, chemical properties. The main chemical property is combustion. As we all know, carbon burns in oxygen to give carbon dioxide along with a lot of heat and energy. A simple combustion reaction is shown here. Hydrocarbon plus oxygen giving carbon dioxide, water and heat and light. The peculiarity of combustion is saturated hydrocarbons combust and unsaturated hydrocarbons combust in 2 different ways. As you can see, saturated hydrocarbons gives a clean blue flame. The picture shows a gas stove burning. This is a common thing that we see in our homes. A gas stove burns so since there is sufficiently oxygen rich mixture to burn, which means complete combustion has taken place. But as you can see again, unsaturated hydrocarbons gives yellow flame with a lot of smoke. This is also called sooty flame. This occurs due to incomplete combustion, which means there is no sufficient amount of oxygen here. The next picture you can see is the blackening of the bottom of a vessel. This is due to the reason that the air holes are blocked and the fuel is getting wasted. The amount of fuel is really wasted and it is blocked there and the blackening occurs. One of the next main chemical property is oxidation. Carbon compounds are easily oxidized on combustion. Also, alcohols are oxidized to carboxylic acid. As you can see here, ethanol is oxidized to ethanoic acid. The number of oxygen is increased. Substances capable of oxidizing other substances are called oxidizing agents. As you can see here, you can see alkaline KMnO4 written. This is the main compound which is responsible for oxidizing ethanol to ethanoic acid. So, alkaline KMnO4 is an oxidizing agent. Next, addition reaction. As the name suggests, this particular reaction adds some compounds or some atoms to a particular compound. As you can see in the picture, alkene is an unsaturated compound. It occurs hydrogenation in the presence of nickel as catalyst to add hydrogens to the double bond. As you can see in the picture, 2 new hydrogens are added. This addition reaction is commonly used in hydrogenation of vegetable oils. Addition reaction does not confine to hydrogenation. Also, there is halogenation, which is addition of halogen to the double bond, hydration, which is addition of water to the double bond, and as we discussed, the hydrogenation addition of hydrogen to the double bond. These 3 peculiar addition reaction gives 3 different products. Next main reaction is substitution reaction. Here, one type of atom replaces another one. Saturated hydrocarbons are generally less reactive, but substitution reaction is a peculiar reaction that takes place with saturated hydrocarbons. As an example, let's just look. In presence of sunlight, chlorine is added and replaces hydrogen to a saturated hydrocarbon. In the example here, you can see methane CH4 plus Cl2 in H2, which means it is occurring in the presence of sunlight. It is giving CH3Cl plus HCl, which means one hydrogen atom is replaced in every step, and finally CCl4 tetrachloromethane is formed. This is substitution reaction. Ethanol and ethanoic acid. Till now, we discussed different categories of hydrocarbons and also the functional group that plays a key role in organic chemistry. Among this, ethanol and ethanoic acid are the 2 different kinds of hydrocarbon compounds that plays a major role in our daily life. Ethanol, CH3CH2OH. It is liquid at room temperature. It's an active ingredient of all alcoholic drinks. Also, it is used in medicine since it is a good solvent. Consumption of small quantity causes drunkenness. Intake of pure ethanol is really lethal. We will die. Long-term consumption leads in health problems. Also, different forms of ethanol include absolute alcohol and rectified spirit. Coming to the reaction. On reaction with sodium, it liberates hydrogen gas and forms sodium ethoxide. As you can see, CH3CH2OH plus Na giving CH3CH2O Na plus hydrogen gas. Also, heating with excess concentrated sulfuric acid, dehydration occurs and it forms ethene. CH3CH2OH plus H2SO4 gives C2H4 ethene molecule plus water. Ethanoic acid, CH3COOH. It's also called acetic acid. A 5 to 8% of solution of acetic acid in water is called vinegar. It's a weak acid. As you can see, the melting point of pure ethanoic acid is 290 Kelvin, which it freezes during winter in cold climates, hence the name glacial acetic acid. Coming to the reaction, the main reaction is esterification. Esterification is a common reaction of acid and an alcohol to give an ester. Ethanoic acid and ethanol react to give an ester which has a pleasant smell. This pleasant smell is used in making perfumes and flavoring agents. Esters reacts in the presence of acid or a base to give back the corresponding alcohol and acid again. This process is called saponification. As you can see, the ester reacts with water in the presence of acid to regenerate the old carboxylic acid and alcohol. Next one is reaction with a base. Ethanoic acid reacts with sodium hydroxide to give a salt and water. This is a typical reaction of acid and a base, neutralization reaction. Similarly, reaction with carbonates and bicarbonates. Ethanoic acid produces salt, carbon dioxide and water. CH3COOH plus Na2CO3 giving CH3COONA plus CO2 carbon dioxide plus H2O water. Similar is the case with bicarbonate. Next, soaps and detergents. These two substances are the main things definitely that we are dealing in our daily life. Soaps chemically are sodium or potassium salts of long chain carboxylic acid, as you can see here. The long chain carboxylic acid are defined as the length of the carbon chain is more than 15 carbon atoms. Sodium stearate, potassium stearate are having a number of 17 carbon atoms in their carbon chain. Soaps are prepared from natural oils by saponification process. Dirt is oily in nature and is immiscible with water. As you can see in the picture, there are two different ends for a molecule of soap, the ionic end and the nonpolar end. The ionic end of the soap dissolved in water, it is hydrophilic. The carbon chain dissolved in oil, it is immiscible with water, it is hydrophobic. Coming to the cleansing action of soap. Soap on mixing with water forms a concentrated solution and it causes foaming. The long non-polar part gravitates towards and surrounds the dirt and absorbs it. As you can see, these are several kinds of and several number of soap molecules which orients in such a way that the oily dirty molecule and the oily dirty non-polar part of the soap attracts together and the dirt is trapped inside that number of molecules by the molecule forms and orient itself to forming a different kind of structure which is called micelle. A spherical aggregate is formed. This aggregate is called micelle. The short polar end turns the water away from the earth, as you can see in the picture. The dirt is captured by the micelle and it is suspended in the micelle and is easily rinsed away. As you can see in the picture, this is a depiction of the thing that we discussed now. Dirt is on the cloth. There are several soap molecules here. The soap molecules orients and forms a spherical aggregate such that the dirt is absorbed inside and suspended in the micelle. And totally the soap molecules are washed away and the dirt is removed from the cloth. Detergents. Coming to detergents, there are chemically ammonium or sulfate salts of long chain carboxylic acids. Soaps are sodium and potassium salts, but detergents are ammonium or sulfate salts. They are prepared from petroleum hydrocarbons. Their chargents do not form insoluble precipitate with calcium and magnesium in hard water, but soaps do. Soaps can form precipitate with calcium and magnesium in hard water. Detergents will not do so. Hence, detergents remains unaffected in hard water. Detergents are mainly used to make shampoos and products used for cleaning clothes. As you can see in the picture, this is a normal detergent molecule. Now let's just compare what an soap and detergent is. Soap, they are sodium salts of long chain carboxylic acid, whereas detergent are ammonium and sulfate salts. Also, detergent also form sodium salts of long chain benzene sulfonic acid also. Soaps are obtained from natural resources like vegetable oils, fats, etc. Detergents are obtained from synthetic materials and hydrocarbons of petroleum. Calcium and magnesium salts are insoluble in water for soaps. Calcium and magnesium salts are soluble in water for detergents. In the case of soaps, precipitates are formed. Soaps produces scum in hard water which affects its cleansing action. This is not seen in detergents. Soaps are biodegradable. Detergents, on the other hand, comparing with soaps, is not too biodegradable.